Hello everyone. In the last video, we introduced to the concept of leakage power. Let us try to conclude it over here. So the basic concept is when we say that the NMOS is turned on, it is at that point of time when the gate to source voltage exceeds a threshold voltage VT. And why do we say so? Because at a voltage which is greater than threshold voltage, we have ample of carriers, ample of a majority carriers that leads to a current flow between drain and source. So at a voltage which is at a gate to source voltage which is greater than VT, you see a current flowing between source to drain, between drain to source, and that's when we say the NMOS is turned on. Similarly, or ideally, we should say the NMOS is turned off whenever your gate to source voltage goes below VT. So whenever your gate to source voltage goes below threshold voltage, ideally we should have said that the NMOS turns off. When we say NMOS turns off, there is no more current which flows from drain to source. That is what an ideal NMOS should behave. But in a practical scenario, what happens if you see this small area over here near the VT? You see a small finite amount of current that still flows whenever we are below VT. That amount of current could be very small. It could be in terms of picoamps and so on, but still that amount of current flows whenever your NMOS turns off. This is also true for PMOS. So whenever your PMOS turns off, there will be some finite amount of current that flows below threshold. So that particular value of current, that particular term is referred to as subthreshold current, and this is what is resulting to a leakage current, or to a leakage power dissipation that is happening across these devices. So that is a very small amount of power, but still that is a finite amount of power when you calculate it across one buffer. So similar currents also flow across all the buffers, or in that case across all the devices which is present on a chip. And when you accumulate that value of current across all the devices or across all the buffers that is present in the clock path, that comes to a significant number. And if you see and the practical example of this is, if you see a mobile phone, if you see a cell phone which you just keep switched off. For example, before switching it on, the battery is like 50%. If you switch it off and keep it for a day or a day or two, if you see that the current if you see that the battery get discharged from 50% to, let's say, 40% or 30%. And this is the reason why we see a drop in the battery voltage. So this is the basic reason for that. And now you see what is the impact of this leakage current of this subthreshold current on a bigger device. So this smaller things, things gives you a real picture of the bigger things. So this is how it impacts the battery power. And this particular thing, we call it as static or the leakage power, because this thing happens whenever you are at constant at logic 0 or at constant at logic 1. So this is and this always happens at whenever a device is turned off. So that's why we call it as leakage power or a static power. It's not switching, but it's on a static mode. That's why we call it as a static power. So there will be a separate set of lectures or separate class of lectures which will be talking only about power, only about dynamic leakage, and we will be deriving some equations and so on, which will be quite interesting to know, because power is such a topic that is being driving the latest VLSI trend. So we will be having a separate class of videos or lectures on different varieties, on different kinds of powers, and we'll be looking into some equations and solving some problems. But this is not the right place to do so. That's why we are giving you a brief introduction of the power. So now let us try to look into the next quality check parameter, which is Signal integrity and crosstalk. So this is one thing which is which has been a major concern sub 100 nanometers technology. So and this is the majority, this is the reason for the majority failures of VLSI chips that we see when in a VLSI industry. So this is one of the primary reason that has been happening. So let us try to understand this topic and how it impacts. So for example, you have a clock net, you have a clock tree, and let's say the clock tree. Okay, the clock tree is usually not only built only of buffers. It can be also it can be also built with inverters as well. So let's say we are building a clock tree with clock inverters. So this is the first inverter, and it is connected to a one more inverter, and this we call it as a victim net. A victim net is anything which is a victim which is getting affected. So that let us call this as a victim net, and you have these two capacitors that is grounded. So let us try to call it as a victim net, and there is one more which we call it as aggressor net. So aggressor is something which is creating an issue on the victim. It is that's why we call it as an aggressor. Aggressor which is aggressing something. It is attacking the victim. So that's why we call it as an aggressor net over here. And this is again a clock tree. So we have one clock. We have one inverter over here, we have another inverter over here, and let's say this is going to one flop and this is going to another flop, for example. So this is again a clock path. So let us call this as an aggressor, let us call this as a victim, and this particular net, let us call it as an aggressor net, and let us call this as a victim net. So as we know that the nets or wires, a physical wire has got a physical dimension, it has got length, breadth and all and so on. That's why we have a finite amount of resistance and capacitances on the wires, and that is the reason for showing the resistance over here and the capacitance over here. So now let's say these two nets are placed so close to each other that there is an amount of coupling happening between these two wires. Let us call that capacitance as coupling capacitance, and we know that C is equal to epsilon A by D. So let us try to assume that a majority of the area of this wire is overlapping with an area of the victim. So this is how your coupling comes into picture. This is how you see the coupling capacitance coming over here. So now when we see these nets sitting so close to each other, so what can go wrong, what can happen? So let us try to understand that, or in general let us try to give you an analogy. For example, in a class, there is a classroom of 50 students, and we have divided the class into two parts, one is, and 25 students of each, and it's in the same room. So in one set, for one set of students, for one set of 25 students, there is a professor A who is giving the lecture, and for the other set of 25 students there is a professor B that is giving a lecture, and all this happening in the same class. So you see, whenever a professor B speaks, Professor A could listen it, and whenever Professor A speaks, Professor B could listen it. So this could create an interference between what Professor A speaks and what Professor B speaks. So this is the kind of thing happens when we sit so close to each other. So similar things also happens over a chip as well. Let's see what happens. We are just naming over here. So let's call aggressor A, let's call this as a victim V, let's call this as a coupling capacitor Cm, and these are the grounded capacitors C1 and C2. So in general, what we have seen in the past is a logic 0 or a logic 1 at this point is determined by the notion or by the state of capacitor at this particular point of time, at this particular point. So at this point we have how many capacitors? We have 3 capacitors. We have C1, we have C2, we have Cm. So we have a part of Cm. So in this case, the value at a logic 1 or logic 0 value at this particular point will be determined by the state of capacitor C1 plus C2 plus Cm. and which will be and which will get dominated, the coupling capacitor or the C1 and C2, which will get dominated, that will be determined by the value of this capacitance. For example, if coupling capacitor Cm is much greater than the addition of these two capacitor, the effect of this particular capacitance will be dominant, and what that leads to we'll be seeing very soon. That is basically leads to crosstalk, and we'll be seeing it we'll be seeing it just minutes from now. So, so basic point that I was trying to make over here is the logic 1 or logic 0 at the victim net will be determined by the state of the capacitance which is dominant. In this case, we haven't yet decided on what is the value of this capacitance. If Cm is dominant, if Cm is much greater than C1 plus C2, the state of the logic 1 or logic 0 will be determined by what is the value on Cm. So let's try to move on, and let's try to see the effect of crosstalk over here. So for example, at the input of the victim, you have a 0 to 1 rising edge, and over here you have a 1 to 0 falling edge. Now whenever this signal flows through the inverter, and whenever this signal flows to an inverter, and at this point of time we'll see a fall to rise and rise to fall edge respectively. So when this capacitance are sitting so close to each other, what happens is, now this particular waveform on the victim is trying to discharge. Basically, the capacitance on this particular point, which is coupling plus C1 plus C2, all these capacitances are trying to discharge at this point of time, but suddenly at some time t equal to t1, let's say, it sees a rising capacitance. It sees a rising waveform over here, which is from 0 to 1. So what happens, because of this coupling capacitor, some amount of this charge gets deposited on Cm, which is the coupling capacitor, and you see a glitch over here. A glitch means it tries to discharge, but then it sees the coupling capacitor is also getting charged on the other end of the plate, and it tries to charge, and again it tries to discharge over here. So we'll try to learn this particular phenomena. Since I'm running out of time, we'll try to understand this phenomena in brief and in more detail, and see what happens and see the effects of this particular phenomena on the following networks. We'll try to look all those things in the next video. Thank you.